So, hello, students. Uh, Hopefully, you are doing great and you will find this video lecture in the best of your health. This is our third lecture on Introduction to Information Technology, and we are going to start the chapter number 2 of our textbook. This chapter is intended to study about the system unit, specifically processing and memory. But before going to the processing and memory, we will be having some important topic like the data representation. That is really important in order to understand that how actually the system process the data and how the memory stores the data, right? So there are several objectives of this topic, this chapter. For example, we will be able to understand how data and programs are represented to computer and be able to identify a few of the coding systems used to accomplish this. You will be able to explain the functions of the hardware components commonly found inside the system unit, such as the CPU, GPU, memory buses, and expansion cards. Students will be able to describe how peripheral devices or other hardware can be added to a computer. So you will be able to understand how computers, CPU, and memory components process program instructions and data. So you will be able to name and evaluate several strategies that can be used today for speeding up the operations of a computer. So you will be able to list some uh, processing technologies that may be used in future computers, all right? So these are the learning objectives of this lecture and specifically this chapter, right? So as an outcome, we'll be able to explain how computers represent data and program instructions. So in this lecture, we will focusing ourselves towards this component only, right? So towards we will be able to understand that how actually computer represent data and program. But in the coming lectures from this chapter, we'll see how we can explain how the CPU, memory, and are arranged with other components inside a system unit. Also, we'll see how a CPU performs processing tasks, and then we will be able to identify strategies that can be used today to create faster and better computer in the future, right? So in this lecture, I'm focusing myself towards the first objective, right? That is the explain how computer represent data and program instructions, right? So let's see. So, uh, we all know that the computers today, we call them the digital computers, right? So the computers are called the digital computers, right? Let me just erase this one. Okay, so the computers are called the digital computers, right? And why do we call them the digital computers, right? So the word digital means the computers actually operates or understands the digits only, right? That's why we call it the digital computer. So the digital computers, digital appliances, they all work on a numeric system, uh, they on the digits system, so they only understand the digits. But normally what actually what language we use, so we prefer to speak in English, or we prefer to speak in our native language, like Khmer or German or French or many other languages, right? So we speak in English, for example, and computer understands, the digital computer understands the digits only. So first of all, we will learn that what sort of the digits this computer understands. That's why this becomes a digital computer. And then we will say how we can translate those our language, the instructions in our language, say for example in English language, into the digital form, into the digits, right? So that mechanism, that system is called the coding system, and the process is called digital data representation, right? So the coding system is we will code our English language or natural language instructions into the in form of the digits so that the computer can understand. So the coding systems are used to represent data and program in a manner understood by the computer, right? So the digital computer, as I told you earlier, it only understands two digits, right? So it understands the digits, but what are those two digits? Only 0 and 1, that we call 0 represent the off situation and 1 represent the on situation. Or if speaking bluntly, 0 represent the false condition and 1 represent the true condition. So for example, if you can see here in this electric circuit, right? So electric circuit, if the circuit is not complete, is broken, right? So it is in an off state. So we represent it as 0. If the circuit is complete, circuit is closed, and the appliance is working, we consider it as true condition, or we call it that the circuit is on, right? Similarly, it can also be represented in terms of the storage. Like we have the magnetic storage devices, so where we have two different values. Whenever we are talking about the magnetism, we know that we are talking about the charges. So we have two natures of charges. One is the positive and other one is the negative charge. So we can easily represent 0 as a negative charge, 1 as a positive charge, so that computer can understand what do we mean by that, right? So digital data representation is the process of representing data in digital form so it can be understood by a computer. This process is called the digital data representation, and the coding system is to convert the data into the program to code our language so that the computer can understand. Why? Because computers are the digital computers and they only understand two digits, that is either 0 or 1. That's why we call it the binary system as well, or binary computers as well. So we'll see in the upcoming slides that what do we mean by that, right? So okay, so okay, just a minute. So yes, okay, so what are those digits that computer understand? That is 0 and 1, and we call it binary digit, as they are two digits only. Bi means two, so they are two digits, binary digits. So computer can only understand the binary digits, and in short we call it a bit, right? So what do we mean by a bit? Bit is the short form of binary digit, right? And this is the smallest unit of data that a binary computer can recognize, a signal, single, or zero, one or the zero, right? So if you can see the stream of zeros and ones here, this 1 0 is one bit, another 0 is another bit, 1 is another bit, another 1 is another bit, right? So many number of zeros and one number of 1 0 or 1, that is considered to be as a binary digit, or in short we call it binary bit, right? So the collection of 8, okay, one more important thing is the bit is the smallest unit that a binary computer can recognize, right? Or it can store, or it can recognize, right? So collection of such 8 bits is called 1 byte, right? So what 8 such bits are called, it means the collection of 8 zeros and ones is called 1 byte, right? So byte terminology used to express the size of document and other file programs, etc. So remember, byte is the smallest unit that a computer can access from the disk. Bit is the smallest unit that the computer can store, whereas byte is the smallest unit that a computer can access from the disk, right? So we usually use, for example, if we have we type some Word document that has a size, and we call it how many bytes of the file it is, right? So you usually use this terminology whenever you are going to copy some data from one disk to another disk, from one computer to one USB drive, or you are going to download it. We usually refer this how many bytes of data is there, right? So this is the byte, right? The storage mechanism, right? So but in actual that is the bit, because of the digital computer system, because of the binary system, right? So we convert those bits into the much larger much larger symbols. Like for example, 1000 bytes roughly, it's actually 1024, 1024 bytes makes 1 kilobyte, right? And similarly 1024, 1024 kilobytes make 1 megabyte. These are the units in order to represent the large amount of the data, right? Similarly, 1 billion bytes, or in short, 1024 megabytes, they make 1 gigabyte. Similarly, 1 trillion bytes, roughly, or 1024 gigabyte makes 1 terabyte. And same goes on petabyte, exabyte, zettabyte, and yottabyte. So these are the storage unit that we have nowadays. So we have the if you buy the hard disk, you will definitely ask how many terabyte of this disk is, or you will say how many petabyte of this disk is. So these are the prefixes that are often used to express large quantities of the bytes, kilobyte, megabyte, and all these things, right? So now similarly, when this computer understands only the binary system, it is important to learn about the numbering system, especially the binary numbering system, right? So the binary numbering system is the numbering system, is a way of representing numbers, right? Same as the decimal numbering system that we human normally use. So we use the decimal number system, like for example, the digits, we have the 10 symbols for that, from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 10 symbols. So if we want to represent any number using the decimal number, we do that. For example, if I want to represent uh, 5, 5, that is in this symbol, if I want to represent 54, then what happens, that is, or if I want to represent 536, or if I want to represent 50,490. So these all are the symbols from 0 to 9, but they are used as the combination of these 10 symbols. Similarly, we have the binary numbering system that they use only 1 and 0 to represent all possible numbers. So if we want to represent more numbers than 2, so it means 0 can represent 1, 0 and 1 can represent 1. If I want to represent 2, 3, 4, 5, 6 in binary, so I will make the combination of zeros and ones, so that I can represent those numbers as well, right? So in both systems, the position of the digit determines the power to which the base number is raised. What does this mean? Let's see this example and then we will understand, right? So say for example, if there is a number 7216, how this 7216 is made up actually? This is the combination of 4 different symbols from the decimal numbering system, right? But what is the place value of 6? What is the place value of 1? What is the place value of 2? What is the place value of 3? You might have learned it in your early childhood classes as well, right? So for example, this 6, the position of this 6 is the unit position. What does that mean? The first position, how it is actually the 10 raised to the power of something. Since this is the 0th location, unit location, it is 10 raised to the power of 0. Next is the 10th location. Remember, unit, 10, 100, 1000. So these are the positions, right? So this is the 10th position. Why? Because it is the 10 raised to the power of 1. Then this 2 is of the 100 position. Why? Because this is 10 raised to the power of 2. This 7 is at its thousands position. Why? Because it is to the 10 raised power of 3. And if I have one more number here, that is 10 raised to the power of 4. Similarly, one more number, 10 raised to the power of 5, and goes on, right? So if we collectively write this number, how do we do that? So we write that number 6, we do multiply it with whatever is the power, right? For 10 raised to the power. So 10 raised to the power of 0 is 1, so we multiply it with 1. We got 6 again. So 1, we multiply it with the 10 raised to the power of 1, that is 10. So it is 10. Then we have 2. We multiply it with the 10 raised to the power of 2, that is 100. Right? So we 2 multiplied by 100 is 200. And then 7, this place value of 7 is 10 raised to the power of 3. So that is 1000. So we multiply 7 with the 1000. So 7 is at the thousands location, right? And then we add them up and we got 7216, right? Similarly, if there is a number 1001 in the binary number system, so what is the place value? So the first digit is same, but the base is different now. Here we use the base 10. Why? Because we have 10 symbols in the decimal number system. Here we have two symbols only in the binary number system. So the base is 2. So it is 2 raised to the power of 0. Then 0, it is 2 raised to the power of 1. Then the place value of this 0 is 2 raised to the power of 2. Then the place value of this 1 is 2 raised to the power of 3. If we have one more digit, that will be 2 raised to the power of 4. One more digit, 2 raised to the power of 5, and goes on, right? So then how do we represent these numbers in terms of the decimal? So what do? We 1 multiply by 2 raised to the power of 0, that is 1. So 1 multiplied by 1, that is 1. 0 multiplied by with 2 raised to the power of 1, right? So 2 raised to the power of 1 is 2. So 0 multiplied by 2 is 0. 0 multiplied by 2 raised to the power of 2, that is 4. So 0 multiplied by 4, that is 0. 1 multiplied by 2 raised to the power of 3, that is 8. So 1 multiplied by 8 is 8, and then we add them up. So this 1001 represents the decimal 9, right? So this is how we actually represent binary numbers in decimal numbers, and similarly we can convert this binary decimal back into the binary number system, right? So how actually we do that, we'll see maybe in the next somewhere in the next courses in the next semester, right? So the important thing is we use the decimal number system. Computer understands only the binary number system. So what does it mean? In order to represent our data so that the computer can understand, we have to convert it into the binary. And if the data is the text data, then we have to convert that text data as well. For example, your name, your city name, your country name, your university name, all this is the text data. We have to convert that text data also into the binary number system. How do we do that? So for example, if I say my name is Waqas, W-A-Q-A-S. So what does W mean, and how computer will understand that, what, how to store this W and how to understand this is W, right? So for that, what we do, we have some coding mechanism, coding system from text to the binary data, right? So there are several coding systems. One of them, one of the classical or the earliest coding system is called the ASCII codes. So ASCII, and the full form is American Standard Code for Information Interchange, right? So we have these ASCII codes. This is a coding system traditionally used with the personal computers, and it was introduced by earlier with the personal computers, right? So, for example, let me say, let me talk about A, right? So how do I convert A so that computer can understand this is A? So I will have one specific code for this A, and whenever this whenever I need to write A, whenever I need to translate A, I will say, okay, this is the place value, these are the values for A, this is the code for A, this is the code for B, this is the code for C, this is the code for D. So these are the defined codes, right? So ASCII code are the 7-bit codes, right? So that means it can host 2 raised to the power of 7 uh, characters, or 2 raised to the power of 7 symbols. That is roughly around 128 symbols can be represented using ASCII codes. So 128 symbols, each symbol has a defined code like A, B, C, D, the number sign, plus sign, 1, 2, 3, whatever. All the symbols or the characters, they have specified 7-bit or 8-bit ASCII code that is that is understood by the computer, and we have an algorithm, a mechanism, a mathematical way to convert that into the binary number so that computer can understand. Then 128 total characters are not enough. to represent all the symbols that we use, right? So then this need was identified by the IBM again, and we were having the extended ASCII code, right? Extended ASCII code was of one extra bit, right? So they were of 8 bits. So 8-bit means 2 raised to the power of 8 characters or the symbols can be represented using extended ASCII codes. So what does that mean? So if 2 raised to the power 7 can host 128 alphabets, 2 raised to the power of 8 can represent 256 characters, 256 symbols. So double than that. So extended ASCII code were used widely in the personal computers. Then we have another coding strategy, that is extended binary coded decimal interchange code, right? This is also developed by the IBM, and primarily it was used for the mainframe computers, right? And then again, if we have the 8 bits that can represent only 256 symbols, that is not enough, right? So for example, people from different regions in the world, they use different languages. Like for example, if we talk about English itself uses 26 letters, alphabets, right? 26 capital alphabets, 26 small alphabets. So 52 alphabets are used only in the English. And then there are a lot of special characters that are being used, right? So what if I want to represent German? What if I want to represent Chinese language? What if I want to represent French language? And Khmer, for example, my language, native language, Urdu or Hindi. So there are not enough codes available so that we can represent all the symbols available in almost all the languages of the world. So then this need was also identified, and that was there was the Unicode were introduced. Unicodes are actually the short form of the universal code. So Unicodes are of 32 bits, right? So 32 bit mean 2 raised to the power of 32 number of characters can be stored, right? So roughly, I mean, it's a huge codes. There are huge codes that can represent almost every symbol of every language. So that's why you can see in the web browsers, in the operating system, and in the application programs, you can see you can always toggle among the different languages, because they are represented using the Unicode. So codes are there to represent multiple languages. So even if you have ever used the Google Translator, so you will find multiple languages are being used. I mean, you can translate from one language to another, any of the other language, right? So in order to represent all those characters unique code is given to all possible characters for all possible languages in the world, right? So these are the universal coding standards designed to represent text-based data written in any ancient or modern language. So it has almost replaced the ASCII as the primary text coding systems, right? So for example, Chinese, Greek, and there are several other languages in the world that are being represented using the Unicode, and ASCII codes are almost now obsolete or replaced by the Unicodes, right? So this was how we are going to represent the numeric data, how we are going to represent the alphabets, how we are going to represent the alphanumeric data using these codes. But what if we have the graphical data? By what do I mean by the graphics data? I mean by the still images, such as your photographs or the drawings that you are creating on different application tools. So we can see there are lots of graphical data, a lot of images available on the internet that we use in our daily I mean in many of the documents, right? So how that data is stored and how computer understand that, what I mean, how to store the graphical data into the in form of the computer, right? Or how do we convert the graphics data into the binary code so that computer can understand, right? So what happens actually, let's have a look at this the picture. So this is a you can see this is a two-dimensional picture, right? Two-dimensional means I have number there are multiple rows, multiple columns, right? So two-dimensional images are represented in form of a grid. Grid means collection of rows and columns, and every row and every column represent a small element of that picture. So we call this a small element of the picture as a pixel. So here you can see this small dot is called one pixel, and pixel is the short form of picture element, right? So there are many pixels in this uh, one graphical image, right? So such technique is called bitmap images, right? So bitmap images are used. So these images are made up of a grid of small dots called the pixels, as I explained earlier. So if the picture is a black and white picture or a monochrome picture, by monochrome I mean they only use one color, right? So either black or white. So it is very easy to represent. So I will create one grid like this. Let me just, if I can draw it here. Let's say, for example, if what I will do, I will basically create a grid of uh, something like this, right? And what I'm going to do is this: there are a number of rows, right? This is just a rough idea to give you how actually the graphical image bitmap images are saved. So there are a number of rows and there are a number of columns. Sorry, I'm not very good in drawing the different uh, I mean images. So here is the image. Like for example, if this is a black and white image, and this pixel at the row number one, column number one, row number one, column number one is a white pixel, right? For example, so I can represent it using 1. If it is a white pixel, I can represent it, say for example, 0. And the next pixel, if it is a black, I can represent it as 1. Next pixel, if it is a black, I can represent 1. If it is black, I can represent 1. Otherwise I can 0. So I can just fill it out. So this will convert this whole image into the binary image, and then this binary image will be stored, right? And when you will retrieve it to display on the output device, based on the zeros and one, it will display. All right, so that's how actually this black and white images are stored in the um, computer, or how actually the computer microcomputer understands the monochrome pictures, or the monogram graphics, or the no, black and white graphics, right? So monogram graphics can only be one of two colors, or they just require one bit for storing the color information. So the problem is not with the black and white, the problem is with the colored image, right? So if this is the color image, so for every single pixel, right, that's one component of the picture, we need to store the color information for every pixel, right? So for example, in this example, for example, if it is using the 16 color images in this I mean, if this is a 16 color images, that means we can store the then the color of each pixel is represented using one half byte, that is 4 byte, because it is 16. So 2 raised to the power 4 is 16. We can store this the information, the color information of one pixel using 4 bits. So if there are 1000 pixels, so we require 4000 bits in order to store this image. If there are, say for example, 100,000 pixels in this image, we require 400,000 uh, bits in order to represent this graphical image, right? So 16 color image is not very sharp, very attractive color. So after that, we were having the 256 color image. So 256 color means for every pixel we need to store the color information of each pixel, and we require 256 colors. That is roughly 2 raised to the power of 8. That is equivalent to the 256. For storing the information of color information of each pixel, we require 8 bits, right? And now you can see it is double than this one. So if this image is having 100,000 pixels, so it requires 800,000 bits in order to store this image. And nowadays what we are using are the true colors, right? True colors are 16.8 million colors for 1 pixel. So that means in order to store the information of color information of 1 pixel, we require 24 bits, right? So if this image uh, is consist of 100,000 pixels, so we require 2400,000 bits in order to store this graphical image with true colors, right? So that means the graphical images are very much heavy in size. They consume lot of bytes in order to store the colors. So what is the strategy to do that? We always store it in the true color image, but then luckily we have the compression strategies. We compress the image and that reduces the size of the image on the disk. That's why we can easily transmit over the internet and we can store it in very small spaces, right? Clear? So if we require more colors, we have to increase the number of bits. Now that what you have understood from here. So this is how we actually store the graphical data or the image data, right? So now let me talk about one more thing. That is the audio data. What if I am speaking right now, like I am recording my voice? So how computer will understand that this is the voice, right? How it will understand that this is the audio data? We have to convert this analog signal into the digital form, right? So voice is the analog signal that I am speaking. We have to convert it into the digital form. So must be in digital form in order to be stored on or processed by the computer. So what we do, we actually store the information for multiple, so lot of data is being generated, and audio data requires a lot of space in order to store. So for every second that I am speaking, it require millions of bits in order to save that. But luckily we have the compression strategies. Then those compress this data into the smaller size. Like for example, MP3, right? MP3, we all know that MP3 is a compression technique to compress the audio files. So this is 10 times smaller than the uncompressed digital version. So we can easily transmit MP3 files over the internet, and we can transfer among the different devices, right? Clear? So what if the data is not only the graphic, not only the audio, but it is a multimedia, video data? So how video is processed and how video data is stored? So actually what happens, video is basically the collection of images, right? Video is the collection of images and the voice, right? So what happens, whenever we are going to store the video data, we actually display using a collection of frames, right? For where every frame contains a still image, right? So say for example, if we want to run a video, so normally what happens, we changes the images very quickly, very frequently. Like for example, 24 frames per second means 24 images will be changed in 1 second, and we will see like a man is moving, the video is running, but actually in reality those are the still images captured and stored in the computer or in any mechanism, right? So what happens, so we have 24 still images or maybe 30 still images, and every 1 second we are continuously moving the frames in 1 second, 24 frames or 30 frames in 1 second, so that we see that the image, the person is moving or the things are moving, but in reality they are different images stored and passed in 1 second, right? So since one image require lot, in the previous slide we saw that one image in true color require a lot of data or lot of bytes to store on disk. So now for 1 second video, I'm saying we require 24 or 30 images, right, for 1 second video, right? So you can see for a 2 hours movie or 3 hours movie, how many number of images are there and how many number of frames are there, and then audio data is also there. So that means we require a huge number of bits in order to store the data. But then obviously we can always compress that data. For example, we can convert the AVI files, that are the uncompressed video files, into the MP4 format, MPG format. Those are actually the algorithms to compress the data, and so we can store the 3 hours movie or 2 hours movie in one simple the CD drive, or we can simply store it on the USB, right? So this is how we actually store the data. Clear? And then okay, so what about the software programs, right? So we saw that how to store the text, we saw that how to deal with the numbers, we saw that how to convert them, then text data, then audio data, graphic data, audio data, video data. Now what about the software programs? So if we are going to install a computer program, install a software in our computer, and that software also needs to be converted into the digital form. Digital form means in form of the binary, so that computer can understand. So all the software programs are also converted into the binary format, right? And this binary format, we call it a machine language, that is understood by the computer, language of the computer, language of the machine. So we call it the machine language, the binary language as the machine language. So binary based language for representing computer programs, the computer can execute directly. So computer programs are the instructions written or converted into the binary program or the language, machine language, so that computer can directly execute them. So early programs were written in the machine language. So when in the early ages of the computer, if a programmer want to design a software, it has to it has to write a program in the language of the machine, in the language of the computer, that is zeros and one only. So sequence of the zeros and one. But that is obviously require a lot of skill set, and not everybody can do that, right? But today we are lucky that we have we have a lot of programming language where we can design or we can write the computer software in nearly English language, like visual programming or the visual C or C++ or the Java, and many other programming languages are there. Those are very close to the human language, to the English language. And then what happens, we translate those English language programs software into the binary or the machine language, right? So there is a software that is called compiler, that actually converts the human language or the programming language, high level programming language, into the machine language, so that computer or the processor can directly execute that particular instructions, right? So this is how we are going to represent the data in computer, or in terms of the machine. So what we have learned so far in this lecture, we saw that the computer is the digital computer, and in order what and the digital computer only understand the binary language, that is either 0 or 1. So in order to communicate with computer, we need to code our language in the computer language or the machine language, right? So that is a sequence of zeros and ones. So then we saw that first of all, we saw that the decimal number systems and the binary number system, and we saw that if we are using the decimal number system, how we can convert them into the machine understandable numbers in binary numbers. And then we saw the coding schemes for the alphabets, from the English alphabets into the binary language. So we saw that the ASCII codes are there, extended ASCII codes are there, and then we have the Unicodes are there. And then we saw that, okay, if now we have the graphics data, how we can convert it into the binary or the machine language. So we saw that, and then we discussed about the audio data, then we discussed about the video data, and finally we discussed about the software programs, how that they are also need to be converted into the machine language. So that's all for this video, right? And in the next video we will be talking about what actually is inside the system unit. But before going to that, take a quick quiz on this slide, although the answers are given here, but you can do by it yourself. Take care. We will see you in the next video. Bye.